By Marlene Keitzler. Tautomers are a type of constitutional isomer, molecules with the same chemical formulas but different molecular structures or connectivity. The main type of tautomers are prototrophic tautomers. These tautomers are differed by their protons, and so they differ mainly based on their location of a proton and the location of pi bonds. Each tautomer still has the same number of pi bonds and has the same formal charge. However, the distribution of the pi bonds and formal charges are different based on the different structures. Additionally, for it to be a tautomer, a heteroatom, usually either oxygen or nitrogen, has to be part of the structure. Two or more tautomers, depending on how complex they are, will interconvert in a rapid equilibrium in the system, which is indicated by these double arrows, showing that it's in equilibrium. They will enter in rapid equilibrium, which are interchangeable by a proton transfer, resonance structures, and the other proton transfer right here. Tautomerization is a process of converting from one tautomer to another. This can either be catalyzed by an acid, right here, or a base. So there are two steps, protonation and deprotonation. As shown in the image below, protonation is when the keto is converted to the resonance structure. In acids, the protonation step occurs first, and then it's the deprotonation. It's the opposite for bases, where the deprotonation step is first, and then the protonation. As you can see here, the OH group, it reacts with the keto, taking off the hydrogen, forming an H2O molecule. This is the deprotonation step. This forms the resonance structure, and as you can see, there are two resonance structures, one without a double bond, one with a double bond. So by doing this reaction, it takes off this double bond, and it forms that one, or that single bond. So it takes off the double bond between the oxygen and the carbon. Then this is the protonation step, where it reacts with the H2O, and it gives off this hydrogen, which bonds to the oxygen. Now this is the new tautomer. Then it's the opposite for acids, where the protonation step occurs first, and then it's the deprotonation step. The keto, it reacts with the hydroxide molecule, the hydronium molecule, and it takes on a hydrogen, therefore taking away this double bond in the resonance structure, which then this new resonance molecule reacts with the H2O, and it gives off a hydrogen. So this is the deprotonation step. Okay, and then next, there are multiple types of tautomerization. One is the Ketoenol reaction. The keto tautomer has a heteroatom and a carbon forming a pi bond. For example, oxygen and carbon double bond, also called a ketone functional group, whereas the enol has two carbons forming a pi bond, leaving the oxygen to form a single bond with the carbon, since the number of pi bonds has to stay constant, and therefore the oxygen is forced to form a bond with a hydrogen, which forms an alcohol functional group. The name ketoenol is derived from the functional groups it has. So keto stands for the ketone, which is the O and C double bond. So that's a ketone functional group, whereas enol stands for, the En stands for alkene, which is a hydrocarbon with a carbon-carbon double bond, whereas where the O stands for the alcohol functional group, the OH functional group. Whichever of the tautomers is more stable predominates at equilibrium. Usually the more stable one is the keto. That is because the keto has a carbon-oxygen double bond, which is a stronger bond than the carbon-carbon double bond, making this keto form more stable. However, there are cases where the enol tautomer is favored, and this occurs when the enol is an aromatic compound where the keto is not, or when the keto form has two carbonyl groups. An enolate is the deprotonated or resonance intermediate form of the enol. So that's the enolate right here. This is another image showing basically the same thing, except instead of just showing the one resonance structure, it shows both of them. Okay. So as I said earlier, the reaction can either be catalyzed by a base or by an acid, and that then results in which step goes first. So if it's a base, deprotonation goes first and then protonation. If it's an acid, protonation goes first and is followed by deprotonation. So there are two other types. The one type is an imine and amine tautomerization. This is the equilibrium between imines or shift bases and enamines. This equilibrium system is the nitrogen equivalent of the ketoenol tautomerization. Nitrogen takes the place of the oxygen in the ketoenol reaction since it reacts with the acid molecule, forming a bond with the NH+, causing the double bond to shift from the NC bond to the CC double bond. The third type is the amidic acid amide tautomerization. Amidic acid contains an OH group bonded to a CN double bond. The amide contains an NH2 group bonded to a CO double bond. So as you can see, the double bond switched from between the oxygen and carbon to the carbon and the nitrogen. So my comparison model was comparing this tautomerization reactions to the Mr. Potato Head. So assuming that all the holes were filled up, in order to be able to switch at least one of the facial features, you would have to take off two of the facial features. So let's say you wanted to switch the location of an ear and an arm. You'd have to take both out, you'd have to swap them, and then put them back in. So this is kind of similar to tautomerization, how you cannot, now in order to switch the carbon double bond, or in order to switch the double bonds, from carbon nitrogen to carbon carbon, you would have to first, protonate it or deprotonate it, and then protonate and deprotonate. So, and that's kind of similar to you have to do something first to it to be able to make that switch. And then there are some applications to tautomers. So tautomerization is a reaction mechanism that can be used to form certain compounds. This is useful in fields in organic chemistry where you want a certain type of compound. By altering the environment of a system, you can favor a specific tautomer over the other. Tautomers are also found in all organisms on Earth because our DNA is composed of 4 different nucleotide bases, which each exist in 2 alternative tautomeric states, which are in rapid equilibrium with one another. As stated earlier, there's always one form that is more stable and therefore is favored in the equilibrium system. Therefore, the conventional base structures are the predominant forms and are essential for the base pairing between adenine and thymine and cytosine and guanine in our DNA. Conversion of the more conventional tautomer to the less conventional tautomer is a frequent source of error in the DNA replication. And tautomers are also another example of tautomers are the three common forms of glucose are tautomers since they are rapidly fluctuating between their 2 tautomeric structures in aqueous solutions. Tautomers can exist both as ring structures and as open chain structures. And that's it on tautomerization. Thank you.